I have prepared some slides as, let's say, as a welcome. Okay, welcome talk, and then Tobias Becker, who's already, let's say, already you can see in your screen. He'll give us, I mean, his keynote speech. Okay, so okay, my name is Dimitri Soutris. I have to welcome in PROHEXA, let's say, workshop. It's a HiPEAC 21 workshop. Okay, as you know, I mean, HiPEAC, this edition of HiPEAC conference will be virtual. Okay, unfortunately, we missed. I mean, Budapest is much better than the virtual world. Anyway, maybe sometime in the next future, maybe the next January, I don't know. Okay, we'll see. I have to thank all of you for your participation. PROHEXA is a workshop, okay, which is about the programming environment and for heterogeneous exascale compute systems. This workshop is a result of another workshop organized by European Commission in Luxembourg in October of 2019. Okay, where European Commission had organized a cluster meeting. Okay, and all exascale projects were present. Okay, and European Commission had create some, let's say, clusters, okay, some groups, okay, with projects, exascale projects, which have, let's say, related topics. Okay. So so PROHEXA is organized by 3 exascale projects, okay, which are about programming environment. One is EPIC, the second one is EPIGRAM, the third one is Exa2Pro, Exa2Pro project coordinator. EPIGRAM is have present. I mean, Stefano Marchidis from KTH is a coordinator of EPIGRAM, and EPIC is Antonio from Barcelona. Okay, so I have to thank colleagues for the other projects. Okay, who provide, I mean, their time and their effort to organize this this workshop. Okay, a few words. Okay. Why some motivation? Okay, today, okay, the complexity of the new exascale systems increases. Okay, and this complexity pose, I mean, new challenges, strong challenges, let's say, to HPC developers. Okay. On the other side, there's a tremendous need for advanced programming environment and models in order to increase, let's say, the productivity and also the deployment of new scientific applications in current or in the future exascale computing systems. PROHEXA is a forum, okay, where, let's say, researchers, developers can sit around the table, okay, and these researchers, they have, I mean, experiences, I mean, about programming models, okay, and the runtime system. And the second one is that with PROHEXA, I'm sure that we'll share, I mean, the speakers will share new knowledge, new technologies, and share experiences, which is very, very, very important. Okay. And the last slide before to introduce our keynote speaker is you can see the program. Okay, actually the program consists of 4 parts. Okay, the first one is the keynote talk speech. The second, in the second session, we have an overview presentation from 2 projects, EPIC and EPIGRAM, and in the third and second and third one, we have a overview presentation of Exa2Pro and results and lessons from these 3 projects. Okay, so the idea is, okay, so with overview presentation, I mean, the speaker will share with to people the novel knowledge, I mean, new technologies that that have developed in the corresponding project, while in the other 3 talks, okay, other speakers will share with us, I mean, lessons, results, okay, ideas, okay, or let's say problems, okay, they have, I mean, let's say had during the last 3 years. Okay, thank you again, and so okay, now it's time to to proceed with Tobias. Okay, so Tobias Becker is a vice president of research and development in Maxella Technologies. Okay, we coordinate many international, let's say, projects. And before joining Maxella, has held the positions as a researcher in the Department of Computing, Imperial College London and Xilinx, and he received PhD degree from Imperial College London, a diploma of engineering degree in electrical engineering from KIT, Karlsruhe Institute of Technology. Okay, his research activities cover topics, I mean, apparently for reconfigurable computing, custom accelerators, and in other terms, data flow agents. Okay, data flow and implementation is data flow agents. So today, Tobias, he will present, I mean, ideas, results, okay, about data flow, let's say, agents, I mean, or DFU agents, okay, and I'm sure that we'll learn new stuff from Maxella's side. Okay, Maxella is already involved in many projects in exascale world, the exascale project, and HPC field. Okay, Tobias, the digital floor is yours. Okay, can you hear me?
Yes, thank you for the kind introduction. So let me now try to share my screen, I guess.
Yes. Oh, okay, excellent. Okay. Thank you. Okay.
Okay, so again, thank you for the introduction. And in this talk today, I would like to talk about data flow computing. And in particular, I also want to talk about why data flow is a good level of abstraction for what we're doing, for using FPGA accelerators, and also a little bit of the bigger context of why we're using this technology and where this is leading us. So I'll basically start with a bit of an overview and where we are in terms of Moore's law and how this has brought us to a rise of various heterogeneous architectures and accelerators, not just FPGAs. And of course, this introduces a range of different challenges for application developers in terms of taking applications, existing applications, porting them over to new accelerators, and finding productive approaches that support this transformation. Now, I want to start with a bit of history. What you see here is the world's first computer, or at least it would have been. It didn't get built at the time, but in the 1880s, Charles Babbage, came up with the idea of a mechanical calculation machine. And so his idea was really to support engineering tasks. There needed to be some sort of machine that can calculate numbers and can carry out these calculations even in a programmable fashion. And he came up with this machine that essentially it's just brass wheels and they can do calculations. Now, the interesting thing is that he thought of this as a calculator, but then the mathematician called Ada Lovelace then discovered that a machine, if it is programmable, could really do anything. And that was a very important recognition because there was now the idea that we have a machine that does calculations, but it can do all sorts of things. So it can do, for example, here again, you see a formulation of an algorithm, but maybe conceptually you could even play music or something like that. So this idea was very powerful. And here you see a formulation of one of the first algorithms. And the important thing is that this model is fully sequential, right? So you see that a number of steps are written out to calculate Bernoulli numbers in this case, and it happens one step after another. And it's very important that this sequential model is actually stuck with us to this day, right? So and it's of course supported by the machine model, but it's also very convenient for a programmer to do this. Now, obviously, this technology really started to take off with the invention of the transistor, and then in particular, not just discrete transistors, but also integrated transistors in an integrated circuit. And we can now put billions of these on a small chip substrate, and that allows us to do amazing things. And you're familiar with this graph here, but I just really want to make an important point here is that as we started to make these integrated chips, we've stuck with the sequential model for a relatively long time. And that was for convenience, but also because it worked well. And essentially what the industry did is make a central processing unit, which is essentially a small programmable unit that can carry out calculations. And over the generations, the transistors got smaller and we could put them closer together. So this means a shorter signal propagation. We can then make them faster. Then we can also lower the voltage, and doing that allows you to keep the power in check. And if you do these things together, making transistors smaller, turning up the clock frequency and lowering the voltage, you have a very powerful scaling model that essentially allows you to make this thing faster and faster. And the convenient thing here is that this is really easy from the application developer's perspective, because we just see a simple programmable unit getting faster and faster. And I don't really have to do much as a developer to harness this. It's just that this single unit just gives me more execution cycles per second. Now that worked until the year around 2005. And then we hit a limit, and that was that the voltage couldn't be lowered anymore. And now that is a problem. Now we can no longer get the power in check. So this means the clock frequency couldn't also be pushed up anymore. So we changed paradigms, and that was here in this case, we just started to make more and more cores. So instead of having a single core that becomes faster, I now have essentially cores that are at the same speed, but I'm just using more of them. And now this changes the world significantly for the application developers, because I now do have to change my view and my conceptual model of how I utilize this processing power. I can no longer just have a single threaded application. I need to think about parallelism. Now, in some use cases, that's easier than others. So for example, if I have a web server that has naturally many parallel threads going on, and there's other applications where I just have many different applications or threads running at the same time. But if I have a large single monolithic application, in order to harness this power, I really now need to think about programming in a parallel way, which is actually becomes a big task here in this context. Apart from that, we can just look at this graph and say, but apart from that, the world is still okay, right? So we're still getting more transistors, we're still getting essentially more cores, but there's a couple of other challenges on the horizon here. So first of all, we now know that Moore's law is maybe not necessarily finished, but it's really slowing down. And it's not so much a hard limit, it's an economic limit. It just gets extremely expensive to make these new smaller geometries and making the production lines for this. And for example, Intel took about 5 years to get the 10 nanometer process running. And we also see other things that are essentially slowly holding us back and becoming a challenge here. So it's not just the number of cores and performance. We also have an incredible challenge with the rise of big data that is being produced. Now, the amount of data that we are producing that is really driven by mobile devices, and obviously it started with the introduction of smartphones, and we now have an incredible amount of data that we're producing every year, and that needs to be stored and processed somewhere. So just to give you an idea, just in the last year, 2020, it was estimated that all of mankind produced 59 zettabytes of data. And that is an incredibly large number. I mean, it's you kind of start to lose the feeling what these Greek acronyms mean. I mean, it's, we have kilo, mega, giga, tera, and so zetta is a very large number. And if you just want to conceptualize this by storing this onto, I have to apologize. I don't know why these slides keep automatically jumping forward, so I have to fix that. So if you want to store 59 zettabytes on 6 terabyte hard drives, I mean, 6 terabyte hard drive is very large already, right? You need 10 billion of those to store all this data. Now, what's 10 billion hard drives? If I take standard 3.5-inch hard drives and I stack them all up on top of each other, and then they're about 3 centimeters high, that is a tower that reaches from here to the moon, right? So just 6 terabyte hard drives on top of each other, that's incredible. Now, related to that is that the challenge of energy consumption of not just on the chip level, but also on the entire infrastructure and data center level. As we're building all these data centers, obviously they all need to be powered. And it's now estimated that within 5 years, so by the year 2025, IT infrastructure will produce more than 5% of the world's carbon emissions. And now that is a big challenge, right? So obviously we're trying to reduce carbon emissions. And just for reference, global aviation is about 2%, right? So we're talking about 2 to 3 times that. And obviously data center providers try to sidestep this by associating with renewable energy. So they're trying to go places where you can have cheap wind. But the problem, obviously, that we have with these renewables is that they're not fully reliable all the time. And we need backups whenever there's no wind, and this is usually fossil fuel. So we're kind of back to square one. So we have incredible challenges in terms of not just on the architecture level, but also in terms of the amount of data we're producing and the infrastructure and how we're computing. Now I want to change focus a little bit on and bring the energy challenge back to the chip level, right? So if we look at the energy that is needed for a certain amount of computation, which is what we're interested in, right? We want to compute. And we compare this to the energy that is needed for just transferring data, let's say off chip or to memory. Then if you look at this table here, we have some examples for integer and double precision floating point. You see that the energy to do add or multiply is it's larger than accessing register file. But any other data access, in particular off-chip memory access, is orders of magnitude more expensive in terms of energy than it is to compute. So what this means is that whenever my data isn't local and I have to access memory, then I'm just spending more time and more energy on just transferring data than I'm actually spending on computing. So what this means is data locality and movement of data is an incredible important architectural challenge. And if we don't address this, then essentially we'll create what's called dark memory. So this is just data that we cannot access because we don't have the energy to afford that. Now, obviously, this brings us to the era of accelerators and heterogeneous systems. And so in this case, the term accelerator is a bit of a misnomer, I suppose, because the focus on acceleration would be to just make something faster, where it really is more generally, it's about a more efficient way of computation. Now, obviously, we've seen graphic cards being introduced, or let's say general purpose graphics cards being introduced in the year 2007. So we have NVIDIA GeForce and CUDA. And so that was incredibly important because we have now not just graphics card that can be used for other things that are non-graphics, but we also had a programming model related to that we can use to essentially take algorithms and run them on a graphics card, which is very new at this point. The same time, we had FPGAs making an entry into the market. So Maxella has obviously been spearheading this and releasing commercial platforms and solutions. So one of the first things we did was seismic computations on an FPGA and later financial applications. And of course, we also have built a programming model to support this, which we'll talk a little bit more in a moment. But we also have seen other examples of other environments where FPGAs are making an entry. So we have, for example, search being accelerated by Microsoft. We have, for example, Google made an entire custom chip for essentially AI workloads. So there's a tensor processing unit. Then we have seen FPGAs even entering the cloud and the data center with Amazon, both Amazon and Xilinx launching new platforms. Now, all of this is very interesting. So we now have a large range of different platforms that we can use to accelerate applications and to do more efficient computations. But what this means from the developer's point of view is we really have to change the way algorithms work, and we have to change the way they are coded and mapped to a compute platform. So we can no longer just take a simple legacy code. We really have to analyze the code. We have to understand where the computational intensive parts is. And then we have to write some new code for the part that is to be accelerated. And when I'm moving from one, let's say, acceleration platform to another or to a new generation, I potentially have to change all this code and then reanalyze, reoptimize. So there is a big task here for the software community and the application developer community to harness this technology requires a lot of extra work that we didn't have in the old days. So that's essentially the world in front of us now. So the important here is that we need a model of computation that is suitable for this task. It needs to be conceptually understandable and relatable to the developer, and it needs to be efficient in terms of mapping to the technology. And this is where we introduce the idea of Dataflow. Now, let's think about how we efficiently can process a very large workload of, let's say, something that has a fixed characteristic in terms of an algorithm that does the same thing on just a very large scale. Now, we're already familiar with how to do this in general, right? So when we mass produce items, we don't necessarily make them one by one. So we can, for example, if we take cars, we could say, well, this is an embarrassingly parallel problem. this could be very easily parallelized, and I have 1,000 workstations where each worker just makes their own car in parallel, right? So that would work. But of course, this is very inefficient. The workers are then still general purpose, and they collide on the way to the storage where they need to get parts. So of course, a more efficient way of doing this is an assembly line. So it is essentially an ultra deep pipeline where the product moves forward, and I have specialized workstations where things are put together at exactly the right time and the right order. And I get essentially parts coming into the pipeline and final results coming out at the end. Now, this model mapped to, let's say, concrete, computational model looks a little bit like this. So when we are building these data flow pipelines, essentially what we're doing is we have a data input at some point, and then the data moves through a number of functional units, computational units, and they are sort of interconnected in a way that is directly driven by the structure of the algorithm. These functional units are specialized to what they need to do. So for example, if I have a square root operation, then I might have a special unit here to do maybe just an approximation of a square root. And so all of this is connected in a way that data movement is now minimized. So as you see, there is no longer access to main memory. The only thing I'm doing here is sending in data which comes from main memory in the first place, of course. But then data just travels between these functional units and goes from one to another. And each unit consumes the outputs from the previous unit. So this really minimizes data movements. And it goes a long way to addressing this challenge of energy efficiency of data transfers. Because here, data transfers are reduced to a minimum. They only have to, there's one place where they would have to go, and there's no intermediate memory or storage. The other thing that is very nice about this model is that it's not just efficient in terms of computation, it's also efficient in terms of, let's say, development and productivity, because it allows us to conceptualize the computation and reason about performance. And as I will explain a little bit more in the coming slides, the understanding and reasoning about the performance, that is what we propose is a central point to being productive as a developer, right? So obviously we have to grapple with this challenge that we want to have high-level development approaches, but we also need to sort of have an understanding of what's going on, because if we don't have an understanding, then it becomes very difficult to optimize the solution. So this is our data flow model. And of course, this maps really well to FPGAs. So as you can see, we're really approaching this not just as an FPGA first technology, but the FPGA kind of follows the programming model. Or in other words, we could potentially even have other chips that do data flow computing. It's just that FPGA is the most efficient platform at the moment. And the reason for this is that the FPGA, of course, is a completely flexible compute substrate that just it doesn't have pre-built programmable or pre-built CPU cores. Instead, it just has programmable logic units and small DSPs and memories. And with this, I can then realize these pipelines. So the FPGA is a good substrate to build these deep data flow pipelines. And then in terms of to carry out the computation, what essentially happens is I can either send data from the CPU side, so this would be CPU memory, through the FPGA back into CPU memory, or it could be from local memory that either consumes or produces data. I can connect it to other cards through a so-called max ring, so to stream data from one to another, or I can connect it to networking. So as we'll see later, this technology is also really suitable for stream processing or processing of network data, because it fundamentally maps well to the concept of moving data or constantly moving information. Now, when we are on an FPGA, the advantage is that FPGAs enable a whole range of dedicated optimizations. So these are things that I wouldn't necessarily be able to do on a CPU because the CPU isn't flexible enough in this sort of way, or it simply doesn't support a certain type of operation. Now on an FPGA, for example, what I can do is I can rebalance between storage and computation. So just to give you a simple example, so when I want to calculate, let's say, 3 times 7, then, well, you would say, well, that's 21. But you're not really computing this. This is a table lookup. I mean, you learned this at some point in school, and whenever 3 times 7 comes up, you just take this number that you've memorized. When you calculate 33 times 7, now you will do a combination of table lookups and real computations, right? So you do the 3 times 7, but then you also do the shift and the addition. And now it becomes a mix of, let's say, table lookup and arithmetic. And I could do similar things on an FPGA where, for example, in particular things that are hard to compute, like exponentials, square roots, these sort of things, they're relatively unfriendly to compute with, to have the actual arithmetic units. I may be able to just look up results from a limited range from a table, right? So that's an option. In the same way, I can also rebalance between I/O and compute. So for example, when sometimes it might be cheaper to just send things to the chip instead of computing it locally, or the other way around. Instead of, if you have a certain sequence that's predictable, instead of sending that, I might be also be able to do it to compute this locally. I can have completely different styles of arithmetic here. For instance, I can have a serial or a parallel type of arithmetic, where I do either one thing or many in parallel at the same time. I can have a sequential or an unrolled version of this computation. And I can also do fixed point arithmetic. So fixed point, of course, means that instead of the conventional floating point units that are common in CPUs, or well, in CPUs, obviously we have the floating point units and integer. Now on FPGAs, we can have arbitrary number formats. So I can, for example, define a fixed point format with an arbitrary number of integer and fractional bits. And this is really something that is not possible on a CPU. You can emulate it on a CPU, but that's obviously not useful to gain performance benefits in practice. Whereas on an FPGA, changing from a floating point representation to fixed point is something that can give typically quite a bit of a performance performance benefit. Now, as I said, all of this is good and well to have all of these optimizations available, but we need to find the right level of abstraction to do programming and development of this. And of course, there's sort of a number of established models available at the moment. We have, of course, conventional hardware description languages, so VHDL and Verilog, and these are very low level. They allow an incredible amount of optimization, but they're also not productive in a sense that it's just too much work and too complicated to really do application development in let's say, a software-oriented context. We have other high-level approaches, like, for example, OpenCL and high-level synthesis. So whereas OpenCL is essentially focused on having many small compute kernels that can be parallelized. And the idea in OpenCL is that this is also cross-platform, so you could use it on GPUs and FPGAs. Now, unfortunately, well, it's true to conceptually that OpenCL is portable, but in practice, what is a challenge here is that an optimized OpenCL is not portable, and we'll get to that in a little bit in more detail. We have high-level synthesis, which is essentially starting from a more kind of conventional C program, and then using constructs to optimize that into an FPGA implementation. And then we also have Maxella, of course, with MaxJ language and Max compiler. And so even though there's a number of options available here, there are really some fundamental challenges that we still face. And one is that obviously we want to have high performance. I mean, it's important that the final result of my work is fast, right? At the same time, we want to reduce the design time through having some sort of high-level technique so that it doesn't take too long to design. We really need to avoid time-consuming iterations because place and route for large FPGAs takes now more than 24 hours. So I simply don't have the option to do lots of iterations on my my design, because otherwise I'll just be stuck on waiting an entire day for the next compile. And the final challenge is that high-level approaches, they can mask design bottlenecks. So if I start from something like an HLS implementation, it's fine if I can just work with conventional C code. But as I just said, the previous challenge is that, the design iterations take very long. So an iterative approach is not really desirable. And at the same time, we still want to have high performance. We also don't want to just have the final result not being quite as good as it could be. So how do we address the challenges? I want to talk a little bit about the Dataflow design process that we're using. And essentially, it's a process that starts by analyzing and architecting first before we even write a program, right? And it's very important that this is very different from a conventional approach where you essentially write a program and then optimize it. Here we optimize the program first before we even write it, right? And this is very important to be productive here. So the first step would be an analysis where I profile the code, but then I also start to model and understand the loop structure. And as I'll just explain a little bit more detail, the loop structure is one of the most important aspects here that we need to understand. Now, once I know what the computationally intensive units are and where most of the compute is, but also once I know how data moves from one block to another, I will then architect a Dataflow architecture. And this is essentially, before I even write the code, this is just a diagram of computational blocks. And when I develop this architecture, we can do performance modeling. And so again, this is modeling before we even implement this. And here I can very quickly understand whether, for example, this is going to be IO limited or performance limited. And when we do this modeling, it's important to know that FPGAs are very predictable. So it's very different than performance modeling on a CPU. On an FPGA, if, for instance, I have a clock frequency of, let's say, 250 megahertz, and I have 1 billion data items, well, then I know that in a pipeline, regardless of how deep this pipeline is, if this pipeline runs at 250 megahertz, it takes 4 seconds to process 1 billion items. It's as simple as that. And if I have, let's say, 10 billion items and or 10 billion bytes that need to be sent to the chip, and I have a bandwidth of 5 gigabytes per second on PCI Express, then I know that it takes 2 seconds to send this data. So I know essentially what my compute time is and my IO time based on very simple calculations here. Now, once I have an architecture, then we will start to write the program for it. We can then generate and inspect the Dataflow graph, and we can also simulate this. So here at this point, I'm still not hitting compile and do place and route. So all of this runs in a high-level simulator where it's higher level than FPGA simulation. So we have a functional representation of this this behavior, and I'm basically now doing computations with this simulated Dataflow model, and I can optimize it further. And only once I'm happy that it actually does what it needs to do and that is correct, only then we hit the place and route button, and then many hours later we get our FPGA bit stream. A very important part of this modeling here is what we call a loop flow graph. So this is something that we build as part of this analysis stage. And a loop flow graph is essentially a description of the key loop structure of an algorithm. So you see nested boxes are essentially nested loops in the algorithm, and we annotate them with the number of iterations, but also the number of operations inside each box and the number of data elements that are going inside a box. And when I do or come up with an accelerated architecture, obviously I need to have some sort of balance of computation and I/O, so that, for example, when we build an architecture here, essentially we need to do some cut and decide what goes on the accelerator and what stays on the CPU. And fundamentally, we need to have obviously a large amount of compute encapsulated in what goes in the accelerator, but also it shouldn't be too much of an I/O requirement, because otherwise I might be I/O limited. And just to give you a specific example of something that you would encounter, and that is essentially very easy to be found in our model, is, let's say, the following situation. So let's say you have some sort of algorithm which has two functions, and the first function takes 1,000 seconds and the second function takes just 1 second. So now I could just approach this and just say, oh, of course, I only need to accelerate the function that takes 1,000 seconds and not the other function, because the other one, that's a trivial amount of data, a trivial amount of time. And let's say I do this and I accelerate the first function and I accelerate it down to 5 seconds. Now that's a speed up of 200. Now, if I just have this model of accelerating the compute part, then this is where I would stop. And this is essentially the model that you typically have in mind if you just see it as a high-level approach where you're just concerned about compute. Now, this is fine. I mean, I now have 5 seconds of compute on the accelerated block or the accelerated function, and still one second on the CPU. But now I have some data transfer in between. So previously, there's about 20 gigabytes of data. And if all of this stays on the CPU, then it doesn't really matter because it's in the same memory. But now it needs to be sent. And I have now this additional overhead of this data transfer, which is 5 seconds, which slows this entire execution down to 11 seconds. Now, that's still a lot faster than the original time. But if I'm aware of, let's say, my I/O requirements and what's happening here, I may be able to do one better. I can then move this second function, number 2, onto the accelerator itself. And it might be that this function actually becomes slower. So maybe it's not suitable for acceleration so much. And it's now slower and it runs at 2 seconds. But I can now avoid this data transfer. And by putting these two functions on the accelerator, I cut down this additional overhead of this I/O requirement or data transfer. And I now only need to output this final result. And it could be that this is much faster than this first version. So having a model that keeps compute but also I/O in mind is very important for achieving an optimal mapping and output. So I just want to give you a quick flavor of what this would look like for a complex application. So we have Quantum Espresso is a computational chemistry package written in Fortran, and it has several hundred thousands of lines of Fortran code. And of course, this is something that is incredibly complex, and it's relatively difficult to just, take that and just accelerate it just like that. So obviously we follow our process here. We start with some profiling. And if you do this, you see that a certain amount of compute just goes into FFTW, which is not surprising because this algorithm is based on density field theory. So it's transforming things into frequency space and reciprocal and real space. So FFT is a key component here. So if I just look at it like this, then I might say, okay, I need an FFT accelerator, of course, right? And this is easy to do, right? So I can just do one, put it on an FPGA. But if I did that, I wouldn't actually achieve very much. So instead of that, we'll first do our loop flow model. And if we do this, we see this key structure of the algorithm. We have essentially a self-consistency loop. In this, there's diagonalization happening. And in this, there's an FFT. And you see that the FFT loop actually starts with an inverse 3D FFT. Then we multiply with a potential, and then we do a forward FFT again. And there's a lot of information exchange between these blocks. So it makes sense to just draw a box around this and do a complete accelerator for this entire loop. And so now this is our Dataflow architecture. And if you look at it like this, if I do an accelerator for this entire block with the inverse FFT multiplication and FFT, I now have something that has a relatively low bandwidth of data coming from the CPU. And a lot of the information is kept locally on the DDR memory that is next to the accelerator. And this is where the high bandwidth is. So essentially doing the split this way, which is informed by our model, I have a much more efficient accelerator architecture that I wouldn't be able to, and this gets us a lot more performance that we just wouldn't be able to get if we just decided to do an FFT accelerator by its own. Another important aspect is fixed point bit width exploration. So we know that a lot of scientific computations use a floating point as a number format. And this is, of course, because floating point is very good to scale across a very large range of numbers. And floating points is also bad at the same time for FPGAs because it's not very efficient. So what we can do is essentially transform into fixed point. Now, this sounds scary because quite often people think that you can't possibly do scientific computations on fixed point. And but it's important to understand that it doesn't actually matter to have the exact same output. We need to have some sort of output that is good enough. And for that, we need to understand some sort of error requirements. And then we can do an analysis, and then we can do potentially a similar computation that is just good enough in fixed point. So in this case, we have a seismic simulation. And it doesn't really matter to get exactly the same data. We need to have at the output, we need to have the same structural diagram of these field lines that are being computed. And as you can see, in 10-bit fixed point, you can do it. It looks the same. It conveys the same meaning. Whereas in 8-bit fixed points, it breaks down, right? So with the right support of analysis, we can do these transformations. And of course, we have built such tools. So we have our Dataflow compiler, but we also built additional tools to do numerical analysis and transformation. So we have a so-called value profiling library where you can instrument your code and see what value ranges you're actually hitting. And then we have a fixed point library to simulate the transformed fixed point code. And we also have various other performance analysis tools that show you whether the application is anywhere near the optimal point or not. Now, where does this get us? Now, we can deliver high performance and energy. I think this we can show. You could argue that anyone who does a half decent job on an FPGA will be able to get high performance and energy efficiency. And so here I just did a quick summary of various applications. We have weather modeling, we have financial derivative pricing, we have reverse time migration, which is seismic computation. Asian option pricing is another financial application. GZIP and QCD is a physics simulation. So all of them have a significant speed up, typically, some order of magnitude improvement in terms of speed, but also energy. So, so this we can do, but what about productivity? So we have done one analysis on productivity where we developed a GZIP in our Dataflow model. And so this is compared against an implementation in both Verilog, so the traditional hardware design, and also OpenCL. Now, first, when we use the Dataflow model, we have more dedicated optimizations available. So a few of the things that I just showed you in the previous slides, they're not available in OpenCL because OpenCL just has conventional data types. Whereas we use some of these additional optimizations, which gets us some additional performance. So in this case, we found that we are 1.8 times faster than OpenCL, thanks to these optimizations, but also 1.5 times faster than Verilog, and also 15 times faster than the CPU. But crucially, this was done by an intern with 1 month development time. And this is someone who had no previous experience with this sort of Dataflow model and just started working with it, learning how to use the compiler, and essentially developing a competing application that was faster than the OpenCL and Verilog versions. Now, we don't necessarily know how long they took, but the paper seems to suggest that there were 4 people working on this, and they probably, spend quite a bit more time on this, and in particular Verilog. I would, be surprised if this is something that is just done by an intern in 1 month. So arguably, we have something that is very good in productivity here. Another example is the level 1 trigger at CERN. So as part of the experiments, they need to trigger whenever a collision happens. And this involves a lot of processing that captures a lot of the sensor data through first an FPGA array. And the trigger then actually starts the data collection of this event. Now, again, they already had FPGAs. The original implementation was done in VHDL. And again, we had a student who did this with minimal experience and had an implementation working that has fewer lines of code, was done essentially with a lot less experience, and is very competitive in terms of the final results. So if you look at the hardware resources needed by the MaxJ version, that is very similar to the VHDL version. Another very important aspect is scalability and portability. So I mentioned this earlier. Let's say you do all the hard work and you port to an accelerator, like an FPGA. What if this accelerator changes? Let's say you have a newer generation, or you want to go to a different vendor. Now, all of a sudden, your code no longer works. You have to do some work to port it, to re-optimize it. And that's a big problem. So we're investing all this effort into accelerating applications. And whenever my platform changes, potentially I have to now do more work on the code. Now, what we have here is an Asian option pricing application, which is, again, from computational finance. It's essentially the compute intensive part is a piecewise approximation of a cumulative distribution function. And I can do a data flow graph for this, which, as you see, has these 5 kernels, and they have the middle stages, they have large fan outs, so there's parallelisms in there, and the input and output stages, there's only one. So of course I can do a sort of simple design space exploration here and optimize this to my platform. And the optimization here is simply driven by the amount of IO that I have, so the bandwidth to my chip, and the amount of parallel units is then determined by how many resources I have on the chip. But what if I go to a new chip? Then all of these assumptions change, right? And this is a problem because the code that gets written here now has essentially optimization constructs baked into the code, right? So the number of units that are used, this is based on assumptions on the hardware platform. And when I port this code onto a different platform, these assumptions are no longer valid. So what we have done is develop a new API that separates out these hardware specific or these platform specific constructs. And we want to have the compute kernel itself should be completely hardware agnostic. So this is just pure functionality, which is one piece of code. And then we have another piece of code that captures these platform specific aspects. So for example, I would then have some code that tells me what the bandwidth to memory or to PCI Express is. And by separating out these different pieces of codes that are where one part is device agnostic and the other one captures the platform, it makes it much more productive to port this code. Now it's not fully automatic that I can just press a button and say, well, this code is now automatically moved from one platform to another. But as I said in the beginning, doing something very high level or fully automatic might actually mask the understanding the bottlenecks. But by keeping them separate and making them available to the designer, I can now very quickly port this code. So you see here, there's this was originally developed for Max4C, which is an Altera FPGA, which was then ported to Alveo U200, which is Xilinx, of course, to Max 5C, and also, which is also Xilinx and Amazon F1. So there are a number of different chips here, and we can get significant speed up by moving it onto these new platforms. And we only have to essentially tweak the platform parameters, and nothing else in the code needs to be changed. Now, another thing that we're working on is code transformation. So that is essentially allowing developers out of other programming models to quickly get to this point where we do this loop flow structure. So here we have, in another research project we've developed with the Barcelona Supercomputing Center, a tool flow that starts on OMS. So OMS is a task-based programming model. And what we do is we can take this task-based programming model and generate a task graph. Then we can analyze this task graph and find repeating patterns. And if we collapse this, we can essentially automatically produce this loop flow graph, right? So based on my OMS program, I can now get this annotated graph that shows me in each box the number of iterations, how many computations are happening inside, and how much data is moving into this box. So it's essentially a tool that really supports this analysis and optimization step in an automated way. So again, it's not the goal to fully automate a transformation process. It's the goal here is to support the designer with the understanding and transformation and making the right decision. And then we've generalized the same approach in the Exa2 Pro project, which is of course what this event today is about. And we generalized this to start with general C++ programs. And the way this works is that we start first with some instrumentation pragmas. So the programmer would add pragmas to provide some annotations on, for example, data elements that go into a loop. We then use the ROSE compiler framework to instrument the code. And again, we have a similar backend where we produce a task graph and then collapse this task graph into a loop flow graph, which again gives me annotations of computational units in each box, and also IO going into each box. Again, the idea here is to support the designer with making the right decisions, not necessarily doing it all automatically. And finally, what I want to end on is stream processing. Stream processing is essentially something that is very suitable or very related to FPGAs, simply due to the nature of how the Dataflow model on the FPGA works. So here we have a project with the European Exfil in Hamburg, which is a linear accelerator and X-ray laser. So they accelerate electrons to the point where they then become an X-ray laser. There is an X-ray detector at the end, which has 16 sensors that all produce 3,520 images each. And that results into a data stream of 16 times 10 gigabit Ethernet. Now, the way they're using this at the moment is they're just dumping all of this data into a massive server farm and writing it to disk. And obviously, this is also a challenge for them architecturally. So what we've done is we've developed an FPGA solution which can process this data online. So as this detector is producing this data at this very high rate, the FPGA can produce in real time a so-called, what they want to do is a calibration and a peak finding. So they want to see whether the experiment actually produced a hit. And so this can be processed in real time on the FPGA, and I can use this for visualization of the experiments set up while it's being run, which is completely not possible if I'm just writing all this data to a server first. So this is where we are. So obviously we are scaling our computations from Dataflow. We're now scaling into a cloud. We can, for example, in a traditional way, obviously we have our data center with our cards and installations there, but we can now also do the same processing on for example, Amazon F1. And finally, we have a smaller version of this, which is essentially an Azure IoT platform, which is essentially a mini HPC node in a small box, right? So it's a smaller FPGA in a smaller processor, and we can have the same model of acceleration now moving up the stack closer to a data source. So if I have a data intensive application, I can do this sort of accelerated stream processing close to the data source, and I can do it all the way at the backend at the cloud as well. So this is concludes my talk. Accelerators are here to stay. This is the paradigm that I think will guide us in this new world. Of course, the efficiency and speed is the main benefit, but it poses many challenges for application developers, and we really have to have a right mix of abstraction and productivity to be able to harness the power of accelerators. So thank you.
Okay.
This
Okay.
concludes my talk.
Okay. Thank you, Tobias. Okay. 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 Have time maybe for 2 questions. Maybe Tobias, you can see in the Q&A box, you can see a question from Mats. Can you see this question?
I think I probably have to.
So I'm trying to write to read this question. Okay. Q&A at the. You can see this icon. Okay.
Yes.
Okay. Please read and just answer. Answer live. Okay. Okay.
Yes. So the question is, so one of the challenges of FPGAs is that they have a lower memory bandwidth than a GPU. And yes, this is true. I mean, obviously we have, different accelerators for different things. GPUs are actually really good at, let's say, these sort of things like dense matrix multiply. But as I said, we have the model of data flow computing and keeping data local goes a long way to addressing this challenge for the right type of algorithms, right? So instead of just going in and out of main memory, if I have the right implementation, I can essentially get a speed up of the FPGA. The other thing that the FPGA is good at is it has lots of small on-chip memories, right? So I can get an incredible amount of bandwidth on this on-chip memory if that is used the right way. So it's essentially, it's kind of, I would say, different types of things for different problems. I don't know if this is a sufficient answer for this.
Okay.
Yeah.
Okay. Okay. I cannot see any other question from Q&A box. Okay. I mean, the panelists can use, let's say, their microphone if they would like to ask questions. If there's no any other question, maybe I ask just one question from my side, Tobias. Okay, following what, let's say, what Mats asked, okay. Okay, this log starting debate, okay, between FPGAs and GPUs. So I try to, let's say, to ask from different perspective. Okay, can we, let's say, build, how to say, a benchmarks, a data flow benchmarks, okay, or a set of benchmarks which are less suitable for FPGAs, or another set of benchmarks suitable for GPUs. I mean, or application domains. Yeah, this is a yeah.
So is the question to have a benchmark to decide what should go on a CPU and FPGA, or to benchmark the different architectures in their own?
Okay, for a given benchmark or for a given application, I mean, okay, we have to accelerate. So
yeah,
if it is sparse, okay, GPU seems to be the most appropriate solution. If it is let's say like your XFL, okay, it seems that DFE is right, is DFE. So can you make a table, a matrix, okay, to identify I mean, that this application or this or particular domain is.
Yeah. No, there's probably a few things that you can check, right? So one is, as you say, is it sparse, or is it a dense computation? The other one is probably arithmetic. Does it really need to be double precision floating point? The answer is yes, then it's probably better on a GPU. If it can be done in fixed point or low bit width computations, FPGAs are really good. So we see the reason why FPGAs are so good in this AI field is that quite often the neural nets you can do with a low number of bits, right? So that's an important one. the memory access types play a large role, or the nature of the, let's say, if we can, streaming is something that this is relatively unique to FPGAs, right? Yeah, so I can probably have, let's say, a table of tick boxes, right? But this would be like a simple first step guidance.
Yeah.
I think where we really then have to do the work is, of course, this sort of modeling, right? This is what I introduced in how we, start an application. So I'm kind of proposing we have to go with understanding rather than just a high level, tool or box. And I know this seems like, counterintuitive or too much work, but I think if we can at least reason about the high level aspects of an application, then we can guide that in the right direction relatively early, I think.
Okay. Thank you, Tobias. Thank you for your time. Okay, for very interesting, talk. Okay, Dataflow is paradigm is very fundamental. Okay, for Exascale Compute Systems and future Exascale systems. So I have to thank you. So now, according the agenda, we have break. Okay. And in 5-6 minutes we'll start, with session on. Okay, thank you again, Tobias.
Okay.
Okay, welcome back to the PROHEXA workshop. So let's continue now with the second season. Season 2 includes 4 presentations and a coffee break in the middle. So the first presentation is the overview of EPIC, the European joint effort toward a highly productive programming environment for heterogeneous exascale computing. The presenter is Dr. Antonio Peña. Antonio Peña is currently a senior researcher at the Barcelona Supercomputing Center, Computer Sciences Department, where he leads the accelerators and communications for HPC team, and serves, among others, as a technical coordinator of the Horizon EPIC project. He's also teaching and research staff at the University of Catalonia. He's a former Marie Curie and Juan de la Cierva Fellow. Antonio is a recipient of the 2017 IEEE TCHCP Award for Excellence for Early Career Researchers in HPC, and he's involved in the organization and steering committees of several conferences and workshops such as SC and IEEE Cluster. And his research interests are in the area of runtime systems and programming models for HPC, include resource heterogeneity and communications. So, Antonio, thank you. You shared your screen, so I think you can start.
Hello, good morning. Thank you very much for the nice introduction. So, can you confirm you can see my screen and you hear me?
Yes.
Okay.
We can see your
Awesome.
screen. We can hear.
Can you also see my pointer, my mouse pointer, just in case I'm pointing?
Yes. Yes.
Okay.
We can see the pointer.
Awesome. Thank you. So you already read the long title of our project, so I'm skipping it. Thank you very much for that. We started October 1st, 2018, so we are in our last year. We will finish on September, so we are like wrapping up, trying to finalize everything, all the amazing stuff that our teams are doing. We are a kind of big consortium for this level of funding. We are 10 partners. We have SMEs, we have research centers, and we also have universities. Our overarching objectives lie on 3 big pillars. On high coding productivity, this is our main focus. We want the like everyone, right? We're foreseeing these new supercomputers to be more and more complex. So we want to ease the lives of developers, software developers. We don't want everyone to become a ninja coder and an expert of all the different technologies and start polluting the code with low-level optimizations, right? As well, we're targeting high performance, but in the context of high coding productivity, meaning that, of course, there will be some loose, let's say, that way of performance with respect to the peak of, or with respect to what could be accomplished on Ninja programming. But this is our objective, to be to produce as high performance as possible within high coding productivity, which is the main focus. We also aim for high TRLs. We want people to use this. We are accomplishing this. So most of our developments are already in GitHub. And the others that are not is that because they are proprietary from the companies. But we aim for this to be not only on papers, right? And of course, there's synergy awareness. We need this for Exascale, the energy awareness. This is how we envision transitioning to Exascale, right? We aim for high coding productivity. Our idea is that you should write your code once and using high-level abstractions, and that code should run everywhere with high efficiency, perhaps not maximum, but as high as possible, and energy awareness. We're focusing on end users that are not like HPC gurus that don't really care much on whether their code could be running in 1 hour more or less. They just want the job to be done and do their science, their applied science with the results. So it should run efficiently, as efficient as possible, but it doesn't really matter if it goes like 100% peak efficiency, right? So we have a set of components, as you see on the left of this slide. We provide a guided code generation on top of a shared memory programming model that to go distributed can be combined with a distributed memory programming model, or it can go directly on top of a distributed shared memory backend. We run on top of Exascale hardware. We have applications for as demonstrators and also for the co-design. And also we have the corresponding performance tools. We expose two programming models, as I mentioned, and that depends on the specifics of the developers and their tastes and their experience, right? We provide this way of coding explicitly the distributed program model with GASP plus OMS. GASP goes through the network, or we also provide this possibility of just coding OMS, and the Argo DSM backend will go distributed on the network. This is the work package list. I'll go quickly over this, but you have here the pointers, the points of contact. We are the two in the coordination. I'm the technical coordinator. My colleague Susana Vaquero is doing the administrative part. We also have the dissemination and exploitation colleagues. These are amazing, as every others. And we have three technical work packages. They have fancy names, but I will call them with short names from now on for everyone's understanding and quick reference. Work package 3 will be dealing with intranode stuff. Work package 4 with internode distributed research and development. And work package 5 is the application co-design. Work package 3 is led by Xavi Martorell, work package 4 by Valeria Barch, and work package 5 by Stefan Lanteri. And so I was showing before a wheel chart with like abstractions. Now I'll list the specific components and also the objectives of within this project of every different component. So we have OMPSS, as I already mentioned, as the shared memory programming model. We are developing within OMS support for OpenACC and OpenMP accelerator kernels, tasking within the accelerators, energy-aware scheduling, heterogeneous memory management, and for advanced Fortran support. I will go over some of these in detail, in more detail in the rest of the talk, and perhaps even more in the second talk. We have our BSC tools providing integral profiling and performance prediction, visualization of traces. The Argo DSM backend will be integrated within OMSAT cluster, and well, I'm talking future, right? This is almost past already. So it has it's incorporating new fancy features for this integration to be efficient, like queue delegation locking, a strong memory model, and also to be able to access accelerator memory. The GPI implementation of GASP is seeking better or more cohesive integration with OMS that started already in the Intertwine project. And it is integrating to great features like automatic data compression and eventually consistent data types. The parallelware component is the one providing this nice guided code optimization and parallelization that I talked before. Is getting OMPSS and OpenACC support, also OMPSS plus OpenMP acceleration, automatic classification, and advanced Fortran support. We have 5 big applications from different fields, also different data patterns like shared memory, distributed shared memory, data intensive, extreme data. And of course, we run on top of this heterogeneity in accelerators, also heterogeneity in memory that is not displayed here. So we run with offloaded tasks, any combination of programming models that we are developing now that support. Like, for example, you can do some of your tasks, most of your tasks in OpenACC, and only some of those that require like a little bit more flow level coding, you can do them in CUDA, and also with the tasking within accelerators development. And well, these are the logos from the institutions involved, and our challenge was, even if this seems like it will not run right, our challenge was to make it all work together. And so I'm gonna go quickly on the overview of some of the components. I was mentioning this guided code generation. What it does is this is at compile time. It explores your code and gives you advice on how to parallelize it, and where to include programming directives, which directives to include, how to improve the code basically. Uh, apart from support for OMPSS, OpenECC, OpenMP offloading with OMPSS as well, it has been incorporated a new front end with advanced C++ and Fortran support that is already released in the commercial release. As for OMPSS2, as I mentioned, we have been working on incorporating OpenECC support. The main idea of OMS is that it lets you, so by the programmer taskifying complex programs, the runtime discovers the parallelism for you. It had support for devices already, for GPUs and FPGAs, but the support was kind of low level compared with the program productivity that OMS is aimed for in general. So we figured out that OpenCL and CUDA was too low level for today's programming in GPUs mainly. Also, we will be looking at FPGAs. So we included OpenECC for productivity. So now you just in your tasks targeting GPUs, you can just include a few OpenECC directives, and that's it. You're going to the GPU. These features with respect to pure OpenECC, that you have automated asynchronous launching, also automated multi-device, which is a pain in plain OpenECC. And we are already developing OpenMP offloading support as well. This is the idea. If you start from just OpenECC, where you have this directive over here, you enclose your code within a function that will be your task, and then you just annotate your function definition with OSS task device, OpenECC, and then the inputs and outputs, and that's it. This is an outline device task, and every call to this function becomes a task invocation, and it lets the runtime discover all the parallelism and manage this multi-device and everything for you. I'll be giving some results in the second talk. As for the tasking in accelerators that I mentioned before, this is targeting some HPC applications like DNN training or some simulations that show iterative structure in which the same workflow is repeated consecutively again and again. So implementing this with for accelerators with CUDA streams has quite some penalty because the driver has to submit again and again this work to the streams, and it's not for free. We found a nice solution in this CUDA Graphs API, because you can just define the graph and run it again and again with very low penalty. Right now we are in the process of integrating this within the OMS syntax and runtime, and our status is that we are developing compiler support. Changing a little bit of topic, we are working on memory placement as well, and on a couple of lines of research here. This first one is for bandwidth aware placement, targeting NUMA systems. And we are aiming at distributing optimally this shared data across different memory nodes at page level granularity. For this, we use recent hardware support for last level cache and memory bandwidth partitioning. Here you have the point of contact in INSCID. The other one is we target at heterogeneous memory systems, where you have obtained memory DIMMs along with DRAMs. So instead of just this view in which you have your only memory system based on DRAM, and you place all of your memory objects here, you move to a view in which you have more memory subsystems, which may be explicitly addressable from software. We advocate for small DRAMs because they are very power hungry, they are expensive. So you need to do some smart data placement and movement across all the different memory subsystems. And this is what it aims for: maximize performance, minimize energy consumption on these heterogeneous memory systems. Our approach consists of data-oriented profiling to figure out what's the access pattern to the different memory objects, and then a distribution algorithm, is what we call. So we do the profiling by the BSC extract profiler, and then we run from that on that profile what we call the Edgemon advisor. This is a script that outputs an optimized object distribution. We have a runtime allocator that is actually developed by Intel in collaboration with us, that's called FlexMalloc. So this runtime allocator reads during real execution, it reads the optimized object distribution, and the execution is with the original code, no modifications at all from the users, and it figures out the right place. It intercepts the allocation calls at runtime and figures out what's the right place for allocating the different memory objects. Now switching to the distributed work package 4. So we have here this test and development platform. Indeed, we have a mini cluster in EPEEC on alternative technologies in the time that we were writing the proposal, right? We were thinking of AMD GPUs, FPGAs, and heterogeneous memory systems. This is what the mini cluster that we have now, where we run our test and development platform with Jenkins continuous integration, container-based approach with Docker containers, also validation and verification of applications under target API combination. Applications are running simplified tests representing the usage patterns, and also if we switch to GASPI, GASPI is a distributed programming model with full control over the distributed data and also the communication between the nodes. 2 extensions have been developed during the project: a compression library, Comprex, for a better utilization of the available bandwidth, especially for data-intensive applications. This is a lossy compression and works well, for example, in machine learning. Works great to save bandwidth. There's also the eventually consistent collectives for better scalability and collectives of the collectives due to the elimination of synchronization points. I will talk a little bit more in the second talk about this. OMS Argo DSM down here. OMS Argo DSM is a shared memory programming model using coherent page-based memory. It focuses on how to preserve coherence when running with OMS with selective fences. So this, I already mentioned, we developed at OMS at Argo DSM for backend to OMS. We have Extrae as our performance analysis tools to identify bottlenecks of applications. It has been incorporated instrumentation for GASPI, and also OpenSSE is right now work in progress. And there's the integration of GASPI and OMS that already started in Interwine with the task-aware GASPI library that is being refined. I mentioned 5 big applications. You are likely to be familiar with many of these. These are big applications in Europe, as these are used as in a strong code design process in the project, but also as demonstrators of what we are developing. We have AVVPs, Navier-Stokes solver. Diogenes is for computational nanophotonics and nanoplasmonics. Osiris is particle in cell code. Quantum Espresso was already introduced in the talk before in the keynote. It's a set of codes for electronic structure calculations. And SMARF, an HPC implementation of several matrix factorization techniques. They're from different partners, of course. They cover a wide range of fields. They cover different data patterns, compute intensive, data intensive, and extreme data. They have they're written in different programming languages, and also they leveraged different programming models on their starting point. So we thought that with this set of applications, we were covering a wide range of fields and patterns, and so that we would not stack to some smallish niche. As for our technical status and remaining challenges, where are we now? We already released the intermediate software prototypes. We are preparing our final software releases, hopefully with everything that we committed to do. And we will be releasing before the end of the project a user's guide taking into account all the programming environment. Our major challenge, work in progress, is to attain this seamless integration of all of the framework components. And if we go over all of our major objectives, I will summarize now the major actions that we have been doing, like a summary of the status of the project. So we wanted a highly productive shared memory programming model on top of highly heterogeneous resources, including processors and memories, which was high scale ready with high efficiency, also energy aware. So for that, we have developed the OpenSCC support for OMS2, which it's giving a very nice programming productivity. We're preparing a paper on this. We are also incorporating support for OpenMP offloading to OMS. And this tasking within accelerators that has been explored and is already being integrated in OMS. We developed these two heterogeneous memory approaches in strong co-design process with applications, and we deployed a mini cluster of alternative technologies. These two flavors of logical memory architecture that I was presenting. This is the distributed GASPI and OMS, and the GPI implementation of GASPI has been equipped with data compression and eventually consistent collectives. And the integration with OMS started month 24, so it's a work in progress. And the other programming model that the other view of the logical memory architecture is this distributed shared with OMSAT cluster over Argo DSM, where developers just develop OMS and it goes magically distributed. This backport has already been released, and the performance has been greatly enhanced from the beginning with several new features in Argo DSM identified by co-design. Also, we identified a possible pattern that is being explored. We improved this guided code parallelization to help boosting the coding. So Parallelware has been equipped with improved OpenMP and OpenSCC support. Has been extended to OMS and is learning a lot from co-design. There's extensive performance tool support. Extra now supports GASPI, and OpenSCC is work in progress. And we had these compute intensive, data intensive, and extreme data demonstrators that were used in co-design efforts throughout the entire project. EPIC was designed with these 5 applications in mind, and these co-design efforts are being key drivers for our progress. We also wanted to maintain European leadership in HPC programming, not our project, but in Europe. For that, we have been doing plenty of dissemination actions, and we're trying hard to influence standardization bodies like OpenSCC and OpenMP. One of our events that was created and sponsored by EPEEC was this MNHack, the Mare Nostrum Hackathon. This is not a GPU-only hackathon like most of the ones that you're getting publicity. This is open to anyone, not only EPEEC partners. We want to help optimize that in these applications. We did 2 editions. We selected 7 teams in each edition. And unfortunately, we canceled 2020 due to the COVID, and we are right now figuring out what we can do for 21. We know people are doing like these remote hackathons. It's challenging. I'm confident we will be able to make it for 21. Just 2020 was a little bit tight for us to rethink the entire thing. Right? But stay tuned. I'm fairly confident that we can keep doing the DMN hack in 21, and I'm indeed invite all the two other projects presented here to collaborate with us in like bringing their technologies and their teams for mentoring, also for participation. Please contact me if you are interested, hopefully. We developed the programming guidelines within EPEEC. These are fairly generic in some sense, but also in some parts targeting our programming environments. So we divided the programming process in 3 steps: preparation of the code parallelization, creating a parallel version of the code, and optimizing the parallel code in iterative mode. There's plenty of tips in these programming guides. I think they are worth reading. And this satisfactory performance is what we already always have in mind. We don't target like crazy people trying to get 100% of the machine. We target just people trying to run their codes in supercomputers. If their performance is good enough, fine. I mean, we won't aim at them getting 99% of the peak of the machine. Well, finally, well, I think I have one more slide, but anyway, we try to collaborate as much as possible with other projects, like with EPIGRAM-HS, with URLab for HPC, with the POP Center of Excellence, with Maestro, with Accelerate, and now, thanks to this event with Exa2 Pro as well. Hopefully, this is just the beginning of a longer-term collaboration. And the impact that we are seeking to kind of to summarize, to deliver a comprehensive exascale-ready production-level programming environment that covers important segments of the broader and/or emerging HPC markets, like extreme computing, emerging use modes, and extreme data. We will also aim at impacting standard bodies and other relevant international research programs, and also to promote European excellence in extreme parallelism and extreme data. As I mentioned, we're always looking for collaborations and users. This is the link to our code repository. Most of the stuff is there. Some other cannot be because there are some SMEs and there's some proprietary parts. We will soon be forming a users group. That's our intention. We're always seeking for collaborations. And if you are interested in any, just drop me an email, please. And this was it, right in time. Thank you very much.
Thank you very much, Antonio, for the very interesting presentation about EPEEC. Now, I see that there are no questions from the attendees. Any question from the panelists?
Antonio, just a quick question from my side. Okay, I'm sure that in the second talk, okay, present the results. Okay, this is actually the model we decided, let's say, for this workshop, but just very, very fundamental. Okay, in your project, you will use OMPs as runtime systems. Let's say in Exa2 Pro, where I'm working, we use another runtime system in StarPU. So, could you tell me, let's say, what new features you added or will add, let's say, in OMPs, okay, within EPEEC? Okay, just okay, very basic.
Yes.
Okay, thank you.
Sure, thank you. So this one, so OMPs was targeting accelerators using CUDA and OpenCL. We're now enabling OpenSCC and OpenMP as well. We are developing the possibility to do tasking directly within the accelerator without the host runtime system to be orchestrating everything, just to float a piece of work to the accelerator and do tasking inside. This energy-aware scheduling as well, and heterogeneous memory management, plus this like updating support for the latest features of Fortran and C++. Those are the main features that we are doing in OMPs.
Okay, thank you.
Thank you.
Any other question? I see also a question in the chat. I don't know if you can see the question, Antonio, in the...
I cannot, it disappeared when I started sharing. Maybe I can stop sharing. Now I can see it, yes. Are you exascale ready in terms of the programming model being tuned to exascale supercomputer, example Gracia, to run in 22, 23 machines like Frontier, Aurora, or El Capitan? One thing is that when we designed the EPEEC, we didn't know what would come. So it's not specifically tuned for that hardware, but it should be generic enough. So we haven't been able to try on that hardware, but we aim to be ready for that. This is like what I can say for now.
Thank you very much, Antonio. Okay, so I think now we can move to the next presentation. So the next presentation is the overview of EPIGRAM-HS, Exascale Programming Models for Heterogeneous Systems. The presenter is Professor Stefano Markidis. Stefano Markidis is an associate professor in high-performance computing and a docent in computer science at KTH Royal Institute of Technology. He holds an MSc degree from Politecnico di Torino and a PhD degree in nuclear engineering from the University of Illinois. Before joining KTH, he was a graduate researcher assistant at Los Alamos National Laboratory and the Lawrence Berkeley National Laboratory and postdoc at KU Leuven. Stefano won 2 R&D 100 awards in 2005 and 2017 as part of the Carta Blanca and SEALS projects. He's an author of more than 100 peer-reviewed publications. Stefano is the coordinator of the Horizon 2020 EPIGRAM-HS project and KTH principal investigator for SAGE-2 and VESTEC projects. Stefano, I think you can start.
Yeah, good morning, everybody. Thank you very much, Lazarus, for the nice introduction. I want to give you a brief overview about the project, giving you the motivation for the project and how we have been developing. So we are now at the last year of the project. And so we are starting integrating all the results in the complete vision of the project. So the EPIGRAM-HS, as Lazarus mentioned, stands for Exascale Programming Models for Heterogeneous Systems. So with the evolution of HPC architectures towards exascale machine, exascale supercomputer, so HPC systems are using a diverse and quite large spectrum of different kind of accelerators and different kind of memory technology. So a major question that as a community we are facing is which new approaches for programming these new technologies are needed. So the project focus like PROHEXA, like EPEEC, on exploring programming models, and particularly on heterogeneous system in the exascale scale. So this component about the exascale era to very large system. As you know, there's been intense discussion in the exascale community and the HPC application community, whether to stick with traditional approaches like MPI and GASPI and brings to exascale, or to adopt new arising disruptive programming approach. So EPIGRAM-HS is looking at extending existing traditional programming approach towards exascale. So we are looking at how to improve existing approach and make it both for exascale and for a heterogeneous machine. So at the beginning of the project, we met and we designed the vision of the project within all the group, and we come up with a major vision for the project that is driving our development. So the vision is to enable extreme scale application on heterogeneous hardware. So the project itself is very much application driven. So there is this component of the co-design in all project. So how was to develop extreme scale application in the past. So in the 90s and the early 20s, well, the number of machines has pretty much quite a similar architecture, and the system will look kind of alike, and they also look rather homogeneous. So, as a matter of fact, typically there was CPU, traditional DRAM, and then a lot of effort on the network, and also I/O is basically was relying on hard disk and tape. So quite homogeneous system, and also the way to program this large system was quite limited to a small set of programming languages and the libraries to programming the supercomputers. So most of the application will be written in Fortran, and some also written in C. And MPI has been the dominant programming approach for developing the application. So how is the situation today? The situation today is very different. So both in terms of technologies, we see that we have many different kind of technologies that we need to take in account when programming our application. So we have non-volatile memories, and we had bus buffer for the I/O, and then we need to consider, for instance, issues that were important before, but even more important nowadays. For instance, like persistence and coherence. So very highly heterogeneous hardware with very different technologies working side by side. And what is important also for application development is that the number of programming interface has basically exploded to address part of these new technologies. So we have CUDA, OpenCL, SQL, OpenCC, a bunch of different approach. So the EPIGRAM-HS project stems on the fact of realizing that the difficulty of choosing the approach when developing a large application for a HPC, and simplified also the current status of the programming models environment. So EPIGRAM-HS focus on 3 key issues that are important for exascale computing with heterogeneous hardware. So we have a part of dedicated to the network, in particular to MPI and GASP, looking at how communication works at the extreme scale, but also how can we integrate accelerators and new technologies within the communication part. We also focus on what regards to data placement and how we choose where to put our data in which kind of memory, and in particular on heterogeneous memory, looking initially at the issue of data placement and migration. And then the last topic is how do we program the compute part of the exascale system, compute GPUs and FPH for the project EPIGRAM-HS. So the major 4 focuses of the projects are, as I told you before, we focus on existing dominant technologies like MPI and GASP. These are proven petascale technologies. We know that they are working on the largest supercomputer in the scale on the current largest scale system today. So we are working on extending them to exascale performance. So major focus on EPIGRAM is NPI and GASP in traditional technology. We're also looking at abstract memory device model that is a name that contains a set of abstraction, API, and runtime system technologies. And the goal here is to hide the complexity of programming systems that are very heterogeneous. So we abstract them, heterogeneous system, and hiding, some of the underlying details to improve the programmability of this large-scale application. We also recognize the importance of emerging application, in particular AI, deep learning, and we are looking at how to develop a domain-specific language for developing deep learning application based on emerging new paradigms in deep learning. And we also target FPGA and GPUs. So we want to run this new application using new emerging deep learning application. Dr. Arthur Podobas will talk about specifically about this particular topic today, so I don't spend much time. But so one of the goals is to look at emerging application and how to run them on large-scale system, how to run on a heterogeneous system. And also the work is been driven by challenging pilot application, both for traditional and emerging fields. So in the project, we have the weather forecast IFS code, and the space weather particle inside called EPIC 3D. And then we have NEC 5000, that is a CFD code. We also introduce AI use case like computer virus detection and lung cancer detection to basically demonstrate the capabilities of our programming model environment. The project is structured in 6 work packages. So we, together with the traditional package management and dissemination, we have 4 packages focusing on those 4 focuses that I've been discussing before. So we have a work package focusing on MPI and GASP, so looking at issues with the network, a work package on the memory abstraction model for heterogeneous system, and one work package focusing on GPU and FPGA programming. And there's application and integration work package that is driving all the co-design work in the project. So who are the members of the project? So KTH in Stockholm is leading the project and responsible for the management and dissemination and standardization part of the project. The work package 2 is led by EPCC in Edinburgh, together with the ETH in Zurich. So the network, the MPI part is led by EPCC together with the ETH. We have Fraunhofer leading the work package about the compute, that is GPUs and FPGA. And then we have HPE Cray, Hewlett-Packard Enterprise company, leading the heterogeneous memory work packages. And finally, last but not least, we have ECM WMF that is leading all the work on the application, co-design work, and integration of programming models development into the application. So it's rather compact number of people working in the project. So I will just give you a brief overview of the technologies that we have been developing in the technical work packages. Today, this afternoon, Dr. Arthur Podobas will talk specifically about that one. So I won't be able to go into detail, but please, reach me out if you have any question about a different part of the programming environment of EPIGRAM-HS. So let's look at the first work package that is about network. So as I told you before, this work package is about MPI and GASP. So the first major things that we are looking at in this work package is that development of efficient and scalable collectives. In particular, we are looking at the so-called persistent collective. So an MPI already provides so-called persistent communication when it comes to point-to-point communication. So this doesn't exist in collective MPI collective. So what we have been doing is to design, develop, and implement new MPI persistent collectives. So what is the reasoning for developing persistent collectives? Is the same one that the same reasoning of establishing persistent point-to-point communication in MPI. So that is established to know before actually start communication, to provide details to the MPI runtime about the topology of the network, if the application is using any specific optimization for those applications. Initiate, making sort of a plan about collective communication in the application, and reuse the plan in all the calls that on the collective calls that application is actually doing. So the goal here is to support complex high level. So these are collective communication patterns that are important for applications. So we have been looking at those collectives that are used by application. Using simple, also integrating the part that regards the heterogeneous part. So using also simple low-level hardware offload instruction suitable for FPGA. So here there's been quite a lot of work, both in design, developing, and implementing, but also interacting with the MPI forum and the standardization forum, the standardization body of MPI, giving feedback as part of this. And now the persistent collectives are being standardized. The second, so the first topic is really to look at high-level communication patterns such as collectives and improve them to Exascale, but introducing this kind of a plan for the FT collectives. Very much like in the FFTWs, where you first run a plan, you understand what is the best configuration, and then you use the same configuration for performing the FFTW. Here we do the same for MPI. So that's the first major topic. The second major topic that we have been quite active on is GPU MPI. So in the GPU MPI, the basic concept is to treat the GPU threads as like a normal course. So if you think, for instance, CUDA threads, we associate each CUDA threads to one MPI rank. So that also means that once you have an MPI application, what you do, you have divided in MPI ranks. You're right away capable of running on the GPU. Right? So since each MPI process is matching one CUDA threads. So this is a major big step for us, because allow us to use directly any MPI application right away on the GPU without any modification. The last topic that we are looking at network and communication for Exascale is the development of non-blocking GASP collectives and communication with the FPGA. So this is working on direction of avoiding additional copies by in-place sector reduction in the GASP segment. So GASP is a one-sided programming system using segments that are basically windows. And these segments are being used in the collective communication. So the first implementation use additional copies to allow the collection communication. The GASP team now has been developing in-place reduction operation. These also include the usage of more advanced technique in the implementation of the GASP collectives, like double buffering and non-blocking execution. This is the work that we've been doing when it comes to specifically about MPI and GASP. The work package 3 is focusing on heterogeneous memory, and particularly how to program heterogeneous memory. The major results of the project is a big, what we call abstraction model for a heterogeneous system that we call Mamba, that is array-based abstraction for heterogeneous memory system. So the Mamba includes an abstract memory models of heterogeneous memory, including particularly looking at tiling and how to match tiling to different part of the heterogeneous system. It includes array-based data structure. So you recognize that the data structure, the data layout that is most used in scientific application is array-based. So in order to support scientific application, is going for array-based data structure. It provides an API for the data allocation, transport, and access of the data. It provides also an API for memory allocation on diverse memory, including, for instance, GPU memories. It provides a cost model API for data movement and access, and that is for to support the data movement and data migration across different memories. And most importantly, is also provide the Fortran API. So our Fortran application, including the project, can also use it right away. So here is basically a diagram of what I've been explaining very briefly here. So we start from the original user program. The way to work on with Mamba in the application is to code, annotate part of the code, also call some functions that are provided by the Mamba API. So that so we annotate the code. We can use calls from the API. And then we have memory tiling abstraction that consists of static analyzer, code transformer, and implicit tile API. So this, when it comes to here, this is basically a compiler technology, and this work is basically done by HiPEEC. So together with the compiler part, the Mamba also has a runtime part that works once we have the executable coming from the modified user program. Here we can provide runtime parameters. So for instance, what is the usage, and what is the info about from the cost model to determine the data movement across heterogeneous memory. So this is I just briefly mentioned the work that we've been doing in heterogeneous memory, particularly data placement and movement using this Mamba API and memory abstraction model. And the last technical work package is the one that is regards heterogeneous compute. So it looks at GPU and FPGA. And so there's a work on extending GPI space that is a runtime system, task-based runtime system developed by Fraunhofer. Before the project, there was very limited support for GPU programming. So the goal here is actually to fully extend the GPI space for GPU programming and specifically for FPGA. So here we have now a prototype with a new architecture of GPI space. This includes additional features that is compared to the production version. So this is introduce a more loosely coupled components. So this means that before EPIGRAM-HS, the accelerator part was highly integrated in the GASP runtime. So it was somehow difficult, to plug, for instance, a new accelerator and use a GPI space. So that led to develop more loosely coupled or uncoupled components for the GPI space, and also introduce the concepts of resources hierarchies that was missing in the GPI space. So together with this new GPS architecture, there's also been a big announcement of the production version of GPI space that now supports multiple implementation for distributed FPGAs and GPUs. This is a major part of the work. The work that Dr. Artur Podobas will describe today, specifically today, will give a lot of technical information will be about a DSL for emerging deep learning approaches. So when I'm talking about emerging deep learning approaches, I'm talking about new algorithms that are neuro-inspired, so inspired by the human, well, by the brain, and this has major advantages when it comes to algorithms and scalability of the algorithms. It turns out that many of these brain-like neuro-inspired algorithms, they do not use collectives. Instead, they are the learning mechanisms comes through local interaction of different processes. So these new emerging deep learning approaches, they display and expose a more local communication between the processes avoiding global communication. So we have been seeing this as a good promise towards exascale. So to switch also algorithmically to avoid collective communication. One important point is also that we are targeting heterogeneous hardware. So the DSL that we've been designed and implemented is supports GPUs backends and also FPGA backends. So one important point is this is very new. Is a Keras-like. The Keras is a TensorFlow or TensorFlow DSL. But the major thing here is that we are using new approaches, and also we support FPGAs. So finally, the real driver of the project are the scientific application. So we have two major Fortran applications that are driving the project. One is IFS, that is numerical weather prediction code. This is Fortran 90 plus using also C libraries, MPI and OpenMP. And what we're looking at is special kernels of many apps of the application, and particularly spectral transform, that are the part of the code that takes considerable time. And some of the physics mini app, for instance, radiation. So that's one. And then the second one is NEC 5000. That is also Fortran, but more specifically Fortran 77. So it gives a little bit more trouble. And so 70% is a Fortran, and like I would say also here is 30% C when it comes to the communication part. So one thing we have been doing also is to change some of this communication from Fortran to C, and also using MPI. So this is also large-scale application, and the challenge here is coming, I would say, from using. First of all, the big challenge is this is a huge code. The second one also the Fortran part. So many of our programming approaches need to consider to be deployed in the Fortran application. We also have HiPEAC 3D code, that is code for space physics and space weather. Here, the major computational cost is moving particles and solving the Maxwell equations on the grid. The application is developed in C++ and supports MPI and OpenMP. And finally, we include two applications from the AI part, and so these are two classification problems. We're using this problem to basically understand what is the improvement from our new developments. So the two applications are the lung cancer detection and malware detection. Right? So given a set of images, we can do segmentation of, for instance, of the lung, and then say, classify there is cancer or no cancer. And so that's the first application. The second one is given a binary, some with the malware and some are not, understand which one has been affected by the malware and which malware it is. So the application have been driving the co-design work. So here is a table with the x-axis, the programming environment work packages, sorry, in the y-axis, the programming environment work packages. And on the x-axis, we have the application and so on. You see that we try to cover pretty much all the spectrum here. So one important part of the project is the standardization, particularly when it comes to MPI and GASP. So we have been proposing and bringing forward in the MPI forum, where we have quite high representation from EPCC, ETH, and KTH, proposal for persistent collectives and partitioner collectives. In addition, there have been quite a lot of support for the GASP forum to bring forward the standardization effort of GASP. We've been also quite active in publication and organization event. We had a meeting on structured approach for programming heterogeneous system. As I mentioned before by Tony and Dimitrios, so we also have joint activities with our Exascale project. So we have a memorandum of understanding with the SAGE-2 and Maestro project to basically provide different technologies across the project to try them out and provide feedback. We have been working with the EPEEC joint workshop with event organized by Tony. And then we also organize past mini symposiums with the maestro on heterogeneous memory and data movement on heterogeneous memory. When it comes to impact and exploitation, so most of our impact is coming from work that is being picked up by MPI implementers, so mostly EPIGRAM and OpenMPI. And we have the big, all the development by GPI and GPI space is picked up by industry project, especially in German, and also to provide the material work, especially when it comes to programming models and MPI and GASP, in providing training material for a tutorial section. As I mentioned at the beginning of my talk, so we are now in the third and last year of the project. The project will finish in December. We have been extending of the 3 months the project. And so in the first 2 years of the project, we have been designing specification, and we have all the first implementation in place, and we have been porting the application to a heterogeneous system. So what we are missing now is really the integration of all the different aspects. So the application are now driving the development of integration. So this is just basically a summary of the project itself. So EPIGRAM-HS stands for Programming Exascale Programming Models for Heterogeneous System. Has all these components, so MPI, GASP, GPI space, programming heterogeneous memory with the memory device model, and pilot application. And that's all the overview of the project, and I'm happy to take any question.
Thank you very much, Stefano. We have time for one question. I see no question from the attendees. Is there anyone from the panelists who would like to ask something? Okay, then I have a question. Stefano, in the epigram, what kind of heterogeneous memories do you consider using Mamba? For example, persistent memories or high bandwidth memories?
Yeah, so initially we done quite a lot of work on high bandwidth memories, and so that was, but then those disappeared. So the major focus now is on persistent memory, particularly NVDIMM, and we have access to the system kindly provided by EPCC by the next generation IO. So they have a system with persistent memories that we are accessing and try on. However, I would say that the major work that we've been doing is more looking at diverse memory, in particular GPU memories. So we treat the GPU as an additional memory, and we use Mamba as a way to access GPU memory and compute on the GPU. So just to summarize, so we started all our work on HBM, in particular with Intel Knights Landing. The focus now is on persistent memory with the system provided by next generation IO and GPU memories.
Thank you very much, Stefano. So let's have a break now, and we will come back at 12 o'clock in about 8 minutes for the last two presentations of season 2. Okay, welcome back to PROHEXA. We will proceed now with the last two presentations of the second session. The first one is the overview of Hexa2 Pro, enhancing programmability and boosting performance portability for Exascale Computing Systems. The presenter is Professor Dimitrios Soudris. Dimitrios Soudris is a full professor in the School of Electrical and Computer Engineering at the National Technical University of Athens. He has published more than 500 papers in international journals and conferences, holds 2 international patents. Also, he's the author and the editor of 10 books, and he's the director of Microprocessor and Digital Systems Lab. He's project coordinator and principal investigator in numerous research and development projects funded by the European Commission, European Space Agency, the Greek government, and the European and Greek industry. He's the project coordinator of Hexa2 Pro, and he has served as general chair and program chair in many conferences such as VLSI SOC, Parma, and co-general chair in HiPEAC CSW 2014. And additionally, he serves as an associate editor of ACM Today's. So Dimitrios, please, you can start. Your microphone is muted.
Yes. Okay. Can you hear me? Just for
yes.
Check?
Yes.
Okay. Okay. Thank Lazarus for the long and very kind, introduction. Okay. Okay. So, as the session chairman mentioned, let's say I'm project coordinator of Hexa2 Pro. Okay. Project. Okay. Today in my presentation, I'll try to present, let's say, some results from the new technologies have already developed within Hexa2 Pro, okay, and the impact of these new technologies will be, let's say, presented by this afternoon, by the second talk, okay. Okay, it works. Okay, good. Okay, why? What's the motivation? Okay, what's behind? Let's say, okay, behind. Before what the main reasons? Okay, the main reason, let's say, to start work with to prepare and submit Hexa2 Pro was. Let's say the strategic set agenda and the roadmap, let's say from European HPC, okay, committee, okay, and the idea is the main motivation is to support, let's say, the growth of HPC application, okay, and also, okay, to make a bridge, let's say, between HPC Gold and Exascale. Okay. Some technical objectives, just main technical objectives for this project. Is okay. The first one is to develop, let's say, programming models, okay, and tools, okay, for co-design, okay, the application and with relevant, let's say, relevant platform, okay. And the second technical challenge is, okay, to increase the productivity of development of developing, and deploy applications within heterogeneous supercomputing system. Okay, heterogeneous is a key challenge, not only in Hexa2 Pro but also in the previous two. Let's say the other two. Let's say Exascale projects. Okay. Regarding the social objectives of these projects, okay, the idea is, okay, to let's say to lower the barrier between, let's say, the accessibility of Exascale systems and the industry, or the other way, to make bridges, let's say, between industry and scientific community, and in order to implement, let's say, a really challenge application in Exascale computing systems. And of course, would like, okay, to have, let's say, to increase, to have economic impact okay, to contribute to economic impact by the transition of, okay, to the transition of from HPC to Exascale. Okay. Well, okay. Okay. This is a rather, I mean, typical slide in all projects. Okay. It's a project which consists of 8 partners from five countries. Okay. The project will start 39 months. Okay. Okay, we'll ask, and we already received, I mean, an extension of 3 months due to COVID. This is a rather typical extension. Okay. Fortunately, COVID has small impact. Okay, negative impact, let's say, on the project, let's say, activities. Due to really hard work from the consortium, and they have to, from this point, to really to express my appreciation. Okay, the project will officially will end by end of July. Okay, so within okay, in Exascale Pro, we have, I mean, some specific technologies. Okay, okay. Here in this slide, you can see 2 of them. One is SCEPU. I'll explain what SCEPU, and the second one is StarPU. SCEPU is a skeleton, let's say, skeleton programming framework. StarPU is a runtime engine. Okay, you can see that some partners of Exascale Pro, they are working, okay, in these two key components of Exascale Pro. Let's say more than started working since 2010. Okay, 10 years already, and then another version of SCEPU. I mean, develop, let's say, with, I mean, with XS project, and another project with Intertwine. I mean, deliver the new version of StarPU, and through Exascale Pro, okay. I mean, the main goal is, okay, to develop, I mean, a new version of SCEPU and StarPU. Later, I'll show some the new features of these 2 key components. Okay. Okay. Here is the Exascale Pro stack. Okay. Okay, I mean, okay, you have some inputs, have some applications. Okay, I mean, here you can see the partners, the logos of the partners who will provide, let's say, applications. Okay, in this new project, have applications from environment, have applications from high energy, let's say, physics, high applications from supercapacitors. Okay. So CERT, CNRS, and Willy are the application providers. Okay, we'll develop a high-level API and a couple of software abstractions. Okay, skeleton, etc. We'll develop, let's say, a composition framework and optimizations. Okay. Okay, the composition framework developed by and high-level IP will develop by LIU, and a couple of optimizations will deliver by ICCS and University of Macedonia. Okay, and the other key block of Exascale Pro stack is runtime system, StarPU. Okay, Inria is a main contributor, main developer, and Maxeller will provide, let's say, hardware. Okay, DFE agents. Okay, Dataflow agents. Okay, and DFE agent will be used as accelerator. Okay, and and DFE agents will be, let's say, integrated with ULIC infrastructure. In the next slides, I'll try to say a few words, okay, of these three, let's say, main blocks, okay. Okay, and third one of the partner, okay, is responsible, okay, for the integration issue, okay, for the integration, I mean, work package, okay. Okay, I'll start from Skepu, okay. Here, okay, yeah. Okay, Skepu, okay, as I mentioned, Skepu is a skeleton programming, let's say framework. Okay, the main contributor, I mean, the main contributor in Exa2Pro is Lee Chopping and Professor Christoph Kessler. Okay, okay, skeleton is a predefined, let's say, generic, okay, programming building block with some properties, okay. The skeleton can model a computation, can provide sequential interfaces, and also encapsulate some, let's say, implementation based from platforms, including, let's say, parallelism, heterogeneity, and memory management. Okay, the Skepu provides a set of predefined skeletons. Okay, for example, here you can see, okay, some supported skeletons. Okay, you can see map reduce, etc. Okay. Also, each skeleton is implemented in various backends. Okay, for example, GPU, CUDA, StarPU, MPI, etc. Okay, here. Also they are tunable. Okay, in terms of time and energy. And the last one is Skepu provides STL-based let's say, containers for wrapping operand data. Okay, one vector to the matrix, etc. Okay, good. Okay, here is this is a special case for a more general optimization, and we provide further. Okay. Okay, the for the computation of let's say for example, of a skeleton, okay, can find automatically the expected best implementation, the execution unit. Okay. The automated selection among code variants and resources for execution depend on the execution context, such as the size and the location of opera data. For this point here, I have to highlight this point. Here is for different size problem, okay, which is a horizontal axis, while the vertical is the time. You can see that, for example, for smaller, for small problem size, okay, the same code is okay. OpenMP is appropriate, let's say, selection, while for larger size, okay, CUDA implementation, okay, is a most appropriate one. Okay. So this is a very say nice critical point, okay, to select the most appropriate architecture, okay, depending on the problem side. Okay. Okay, we have developed, let's say, there's a neat method, okay, and to develop, let's say, tools for performance modeling, and okay, and predictors, okay, and these predictors are very, very important in, let's say, for runtime matching where you can select the most appropriate, architecture solution, okay. This is suitable, let's say, for systematic computation scenarios, okay. Now, Skepo supports platform-specific, let's say, user functions variant that can be provided by expert, let's say, programmers. Apart from the predefined skeletons, a user can develop a customized, okay, or customized skeleton, or can modify appropriately a predefined one. This is a very, very nice feature, okay, for Skepo, and we believe that we provide, a lot of flexibility to developer, the user, okay. And this point is a nice feature of Skepo that can nice feature to so in the sense that Skepo can use, okay, in different applications, okay. The corresponding backend, okay, corresponding backend variants are generated and are selectable, okay, if a specific feature is, for example, specialized instructions, or let's say SMMT, are available on the target system, okay. The target system, okay, can be modeled, okay, can be described, okay, can be described by XPDL platform, okay, platform modeling language, okay. This is XPDL, is also provided by Lichopik University. Now, okay, good. Okay, some words about composition framework and optimizations. Okay, actually, the composition framework mainly is delivered by LIU Lichopik, while optimizations and from other partners. Okay. Okay, good. The composition framework, okay, bites every call of a multivariant component, okay, to some implementation variant. Selection of the best variant, let's say, code is context dependent, okay, and the selection could be static or dynamic. I have a, let's say, okay, the next slide, I think, will elaborate a lot more. Let's say the last point. Okay. Okay, here. Okay, you can see here a couple of, let's say, possible implementations. Okay. Okay, with static performance prediction, this, okay, for different platforms, okay. Okay, with let's say with composition framework, okay, and we can and static composition with who has specific, let's say, features, okay, we can deliver, okay, a subset, okay, deliver a subset of, we select, not deliver, we select a subset implementations, okay, which meet specific criteria for the platform. And through, okay, and this for, let's say for example, these 5 possible, let's say implementations will fit, let's say, to runtime system, okay, and through the dynamic composition we select, okay, the most appropriate one, okay, this block, which will be implemented in StarPU. Have to stress one point, okay, static optimization, static composition take place offline, okay, while of course, okay, dynamic composition take place at runtime, okay, or online, okay. This procedure is called, let's say, staged composition. Okay. Now, in the next few slides, I try to explain through very simple slides. Okay, the idea of StarPU and how StarPU communicated with, let's say, the composition framework, and how can make some decisions. Okay. The composition framework may receive performance feedback from runtime systems about the implementations. Okay, about each implementation. The composition framework executes the application in each application, and the runtime system returns feedback. This one, okay. And this enables, static and dynamic composition. Okay, as follows in the next slide. Okay, just have static optimizations, memory management, these possible, let's say, implementations, composition from runtime. Okay, so here, let's say you have, have 6 implementations, okay, which are available through SCEPU. Okay. And okay, were executed all these 6 implementations at design time, okay, offline, in other terms, okay. Okay, and we discard, let's say, 2 of them because 2 of them, let's say, do not, let's say, do not meet, let's say, specific criteria. User specified, constraints. Okay, so have 4 potential, choices. Okay, and these 4, let's say, architectures are selected by the composition framework. Okay, and will provide, let's say, these 4 implementation as input to composition framework. Remember what I mentioned before regarding the static and dynamic composition. Okay, and having in mind the select criteria, the composition framework, okay, provides as output 2 of them. Okay, here. Okay, and okay, these 2 inputs, let's say, these two architecture implementations goes to, say, to runtime, which select the most appropriate one. Okay. Okay. Star, now I'll focus on Star PU. Okay. Okay, Star PU is okay. It's a sorry. Okay. It's a runtime system for heterogeneous multi-core. Okay. INRIA is the main developer, okay, of this runtime engine. Okay, the new features, okay, of Star PU in Exascale Pro are the following. The first one is that the Star PU can provide, let's say, multi-criteria scheduling. Okay. In terms of, let's say, energy, performance, and for example, okay, can offer, let's say, can support, okay, fault tolerance support, okay. I mean, the task graph enable asynchronous checkpoint, okay, and sorry, okay. And the last one is that Star PU, okay, now is can support, let's say, FPGAs. I mean, DFE Dataflow agents from Acceler. Okay. Of course, okay. Of course, can support also other platforms, CPU, GPUs. Okay. I mean, OpenCL, etc. Yeah. Okay. Here is a we try to summarize, let's say, in a single slide, let's say the evolution of SCEPU. Okay. Okay. At the right hand side of this slide, you can see with red color, okay, the new features, okay, regarding SCEPU 3. Okay. So have to only just to highlight that SCEPU 3 can support, let's say, many platforms. Okay, not only CPUs and GPUs, but also hybrid version of them, and MPI and FPGA. Okay, from MaxDFE. Thanks to, let's say, real hard work from let's say from HiPEAC. Okay, and regarding the applications, okay, we have, I mean, 4 applications. One is from high energy physics, okay, from Jülich, in language Fortran C++. For material science, again from Jülich, is the language is the source language is Fortran. I mean, application from CERT, which about CO2 capture. Okay, it's from CERT, and the language is Fortran again. And for supercapacitors and CNRS, the source language is C++. Okay. Okay, the first 2 applications, okay, is already deployed in pre-Exascale. Okay, so we'll try to move further. And for the next, these 2 applications at the right hand, okay, the idea is to shift, let's say, okay, to run this application now, to shift from HPC domain to pre-Exascale domain. Okay, which is the main goal of this project and this initiative from European Commission. Okay, in the afternoon, okay, the second speaker, okay, will provide the results about all this application. Okay, another very nice, let's say, aspect of this project is that we study in this project, let's say, okay, the I mean, engineering software engineering practices. Okay, which is a challenging and very important task. Also, you can see here that there's a lot of applications, okay? There are a lot of studies, okay? Okay, in the last 10 years, so it's very, very important, okay? The majority of this work is related with implementation here, okay? Testing and architecture, okay? And in Exascale, we'll develop a tool for improving the maintainability of HPC applications supporting both C, C++, and Fortran. Okay, this will be okay. We provide, let's say first results, but it's very challenging. Okay, and we believe that to make a bridge between, let's say, the HPC world, HPC applications, and software engineering practices. Okay, we have collaboration here. Yeah, have collaboration with a lot of projects. Okay, projects with Exascale Pro. Project with, let's say, from HPC domain. Here, Evolve is a very big project. Okay, with collaboration with project who have activities, who has activities with software maintainability and another, let's say, clusters, and also have contribution in a couple of roadmaps, especially in resilient EU HPC systems, which already published. Okay, what have a lot of dissemination activities here. I have just to highlight and advertise. Okay, Exascale Pro and I mean EO. I mean EO. Okay, let's say I mean Letter of Excellence. Okay, in France. Okay, we'll organize a joint workshop. Let's say after around 1 month. Okay, will be 3 days full workshop, and here you can see the links. Is free. Okay. Also, we encourage, let's say, our students to participate, because we'll have, I mean, specific sessions with hands-on experience, and yeah, it took a lot of time, okay, to do this work, but yeah, we believe will be a very good training activity. Last point, yeah, we develop, I mean, new features for Skepo, new features for StarPU. We develop the composition framework, okay, we translate actually, I mean, skeletal stuff and high-level abstract, okay, to runtime engine, and to have some first results about software maintenance. Thanks a lot. Thanks, Lazarus.
Thank you, Dimitrios. Is there any question? I see no questions from the attendees. Any question from the participants? Okay, so Dimitrios, I would just like to comment that both the Skepo with the advanced features that you presented and the StarPU also are available in the Exascale Pro website for experimentation. And we're currently preparing some good training material, motivated also by the ECHO and the Exascale Pro workshop on February. So if anyone would like to visit and experiment, is very welcome. Okay.
Thank you all.
Thank you again, Dimitrios. The last presentation of Season 2 is the results and the lessons learned by EPEEC, which will be given by Dr. Antonio Peña from BSc. Antonio, I will not introduce you again. So, yeah, so please, you can start.
Yeah, I cannot share yet because the other presentation is sharing.
Dimitrios, can you please stop sharing?
Just
okay.
Now it's fine.
Thank you. Yes, I think so. Yeah, here it is. Okay. Thanks. So let's go with my second talk on trying to present some results and lessons learned. Unfortunately, we'll have to leave 5 minutes to 1 sharp, but I hope I can give you most of the contents that I prepared. So this is I'm hearing some noise. Okay, now. This is what the outline of what I'm going to present. I'm going to group the results and lessons learned by work package. First, work package 3 intranode, then the internode one. Remember they have fancy names, but this is just for short and for your reference. And the work package 5 application co-design. So. And this is work package 3. This is a typo. It's the rest of the information is good. Starting on work package 3 on this parallelware analyzer tool, remember it was for assisting developers on coding, on parallelizing, on inserting and tuning directives. So one of the lessons learned here is that on the time spent on the different stages of the coding process. So we assume 50% on the coding stage and on the parallelization, and this is where we provide 4 different tools to help people coding, parallelizing. On the tool PW report on high-level overview of the code, PW check to identify defects, PW loops to identify opportunities, and PW directives for the generation itself. 30% of the time is on debugging, and there we provide this PW check tool to identify defects related to parallelism from the analysis of the static analysis of the code. The rest of the time is in the compilation, execution, and performance analysis. We also do performance analysis with the BSC tools. Oh, sorry, wrong key. On the OMSAT OpenECC side, now I have time to deepen a little bit more. So the benefits of joining the 2 programming models is that the user is abstracted from a lot when compared to just OpenECC. OpenECC is already abstract and high level, but bringing in OMS brings plenty of features for programming productivity. So just simple compute constructs, no need for data transfers, no need for asynchronous handling, and no need for like low-level runtime calls like initialization or device management, including and very importantly here, multi-GPU. So we did some, one of the big benefits in terms of performance is the kind of getting free computational overlap because of this task managing. Everything is asynchronous, and the runtime system figures out what to do, what can be executed in parallel, and so it does. So we did some computational overlap evaluation using one of our applications in the project, HiPEAC. I will introduce more details on HiPEAC, then afterwards in work package 5. These are specifically related to this OMSAT OpenECC. So we will show speed up over pure OpenECC, over simple pure OpenECC, that with a simplicity similar to the OMS version. Code complexity remains very low, and programmers only concentrate on the compute constructs. OMS2 takes care of the scheduling and synchronization. Here you can see a lot of overlapping, and basically in this experiment, our evaluation yielded about 3x speed up. With multi-GPU, this remains kind of a challenge compared with highly tuned Ninja coded OpenECC code. But so we implemented kind of what we could to achieve as much of speed up as possible, and results were pretty good. Our original scheduler in OMS2 was round robin across all GPUs, and now we implemented an affinity scheduler to minimize data movement, achieving pretty nice results. Another challenge that we have on performance is that we leverage this NVIDIA unified memory, this vendor specific for the movements, and we're planning on changing that to the OMS runtime because we understand we have more privileged information what data is going to be used next and how when to move it. With respect to programmability, we identified from the co-design process that it was not so obvious to remove use after free problems, right? Releasing memory when it's still to be used. The problem of this becomes on the taskifying model. It's not so obvious on a big code to figure out when a memory is not going to be used by any outstanding by any task that is to be executed, because everything is asynchronous, right? So to prevent this, the programmer needs to identify those risks and insert manually OMS2 barriers in the code. So we're looking at seeing if we can do something about that, but for now it's something that we don't really like that much from the programmability and from the code cleanliness, but this is what we have right now. On another issue on thread safety comes from unified memory and how OpenSCC compilers work. They transform malloc calls to equivalent CUDA malloc managed calls, and this is okay in single-threaded, but in multi-threaded and in the case of OMS, it's not safe to do this, right? Because different threads may be managing memory, and that's not allowed. That's not thread safe. Discussing with the OpenSCC organization folks and with NVIDIA folks, the solution was to set this PRAGMA-ICC set device num so that everything on CUDA malloc managed calls will be done by the same device, by device 0, by the same thread actually in the implementation. Again, we don't really like this that much. We're in discussions with the OpenSCC. We don't know if this will have a solution at all, but unfortunately, this is what we need for now for our applications to work. Maybe a little confusing, but we're working on it and see if we can do something about it. Changing topic on, I'll have time to present one of the two memory management approaches that I introduced earlier. On this page placement for hybrid memory systems. So we are targeting here a hybrid DRAM and persistent memory system, and where should the application data be placed to maximize performance, in this case, to maximize throughput. Our design goals in this work was where to place those pages that were write heavy in the RAM, because the persistent memory has huge penalty for write versus reads, which is much more efficient, and migrate those hot read heavy pages to obtain. This is done dynamically at kernel level without any intervention from the user, without any modifying of the source code, and it exploits the existing mechanisms on the operating system and the hardware. It has two variants. We call this PMP, and there's the variant PMP app, meaning app direct. This is how Intel calls that, when you have exposed the two underlying memory subsystems to the software, and PMP mem for memory mode, when the hardware is doing the memory movements. We have here some results. These are very recent results from our side with this PM benchmark with 80% reads and high spatial locality. And we can see that one of our approaches, the PMP app, beats the others, including the default with memory mode and with the app direct, which are the state of the art provided by Intel. Now switching to work package 4, the internode work package. I'm going to present, I picked one of the works that is being done in GASPI with eventually consistent collectives. They are eventually consistent in two ways. So by dropping some part of the data, which is below some user-defined threshold in a collective, and by exploring this stale synchronous parallel synchronization model, so that some workers can compute some iterations using bounded stale data. Data is not complete. Target are iterative and convergent computations in which you don't really need the precise data, and you can tolerate some slack on the data, on the precision. So as for instance, machine learning. Here maybe clearer. In black you have updates that are visible by all workers, and in green updates that may or may not be visible by all workers. But with slack greater than 1 prevents blocking worker 2. So even if worker 2 hasn't arrived to get all the data from the collective, it does not necessarily block on the collective, so it can move ahead with its iteration. And it has proven convergence for some computations. Sorry, this is the animation, but I already explained. Interesting thing is here on the results. For example, this all reduced SSP collective implemented in GASP in GPI on a matrix factorization with SGD. If you look at the plot in the left, you can see that increasing the slack up to 4 iterations, actually the convergence speed is improved, right? I don't have the data, but I guess that if you improve the slack over that, it doesn't converge, or it converges slower. But up to 4, the convergence speed increases a lot, and the iteration speed, of course, gets that's higher, and you spend much more computation time, that network waiting time. Moving ahead to the application co-design work package. This is repeating my slide in my previous presentation, but I wanted to name again the different applications that we have. We have a VVP for as a Navier-Stokes solver for multi-phase flows. Diogenes is for computational photonics and plasmonics. Osiris is fully relativistic, massively particle in cell code. Quantum Espresso is widely known. It's a set of computer codes for electronic structure calculations and materials modeling. And SMARF is a high performance implementation of matrix factorization techniques. On the first one, on AVP, our colleagues have been working on optimizing its data distribution using our programming models, and like this coloring and distributing. Using this iterative methodology, this iterative workflow, input read, the composition and distribution of data, then the numerical scheme, all this inside, and post-processing and I/O until the end has reached. I don't have time for details, but I wanted to present at least the amazing results that they got on terms of acceleration of speed up to 16x here. These are like 2 different problems: a rocket simulation and a turbulent channel. So they got pretty nice scalability and speed up. And this is also in collaboration with Irene, Joliot, Curie Rome, and the COE Accelerate. On the Diogenes side, our colleagues have been exploring task-based parallelism on a problem with light trapping in a solar cell device. And so this was done first with OpenMP, because OpenPSS was not able to parse one specific feature of Fortran that they had all around the code. We're now about to solve this, but they started porting to OpenMP to start with to OpenMP tasking to start with the process. So again, by parallelizing with tasks, they got the interesting speed ups like this one, 13.5 on 16 tasks. Moving to Osiris and CPIC, this is the one that I was mentioning when I was presenting the OMS at OpenACC developments. Now I'm focusing on the additional work which is outside of OMS plus OpenACC, the other results that they got, which are not less interesting. So these are the two simulation instances used with ZPEEC. This is the LWFA, laser wake field acceleration. This is a very unbalanced case on your left with a moving window, particles concentrated on the right, and most of the action in the middle where the laser hits. And the Wavell, this is the Wavell instability, and it's a very balanced case. So here in the legend, OpenMP serial means optimized OpenMP implementation based on parallel for and reductions, no tasking. OpenMP task-like is OpenMP implementation using the composition of regions, similar to the approach used in OMPs. OMPSS reduction sync is OMPSS implementation using spatial decomposition regions and data dependencies. And OMPSS reduction is same approach as above, but dependencies allow for next time step to start, even if the previous is not completely finished. So in both cases, we can see like the most advanced OMPSS implementation yields very close to ideal scaling and much higher performance than the rest of them. Here, the default, so this is the Osiris EPIC on GASP. The default versions use the checkerboard decomposition, which leads to poor load balancing for LWFA, as particles are concentrated themselves on the right. And rope-wise decomposition works better, though still presents lower scalability than the Wavell instance. But again, we can see that GASP results are very competitive with MPI and beating them. Now we switch to Quantum Espresso again with GASP versus MPI, designed for all-to-all communications. So the number that you're seeing here is the number of nodes after the implementation, MPI or GPI. And we can see GPI again beating its counterside in MPI. Right? We're still identifying the specifics, but this is something that we are seeing repeatedly on all of our tests with GASP versus MPI, and of course the GASP folks are very aware of this, and they have all the details which I didn't have time to include here. For SMARF, our colleagues did a lot of work comparing programming models from the ones that we are leveraging in our project versus others. They did a lot in terms of performance and energy efficiency, program productivity. I grabbed here just some excerpt of all the huge work that Tom and his team is doing. Basically here, what we can see is that OpenSCC yields nice performance if you compare it with pure C on a CPU with Intel ICC and OpenMP or GCC, meaning that just inserting few easy directives, you get speed up just using the GPU. But ArrayFire is giving a lot more performance. Here you don't have the comparison of the programming productivity, which is undergoing, and it will be interesting to see how much it takes you to get from here to there. Also interesting on the CPU part is the Eigen beating this ICC plus OpenMP. Anyway, this is a specific problem in which you achieve kind of low peak performance. There's a lot of data movement and sparsity. But anyway, this is a work in progress. I grabbed some data, and you see how interesting this will be when it's finished. Now this is SMARF. This is again GASP versus MPI. So they examined several web scale datasets and showed that datasets with different properties, like the number of non-zero items per row, require different prioritization strategies. The preliminary results are available, but these results have still to be analyzed. One example in this slide shows strong scaling results for the Amazon Project Review dataset. And the blue line marked the blue line responds to the original BPMF implementation, and the other lines are implementations with posterior propagation and additional parallelization across rows and columns. And the numbers indicate the amount of parallelism across rows and columns respectively. The blue dots indicate Pareto optimal points, and again, in this case, GASPI is beating MPI. So I'm on time. I have to leave. I maybe still we have time for 1 minute, but looking for collaborations and users, our code repository. We'll be looking forward to form a users group, always seeking for collaborations. And here it is my email. Thank you very much for your attention.
Antonio, do we have time for one question? Or
Yes, yeah.
Okay. Anyone from the panelists that you'd like to ask something? Oh, okay. Then, Antonio, you presented results about page data placement in heterogeneous memories.
Yeah.
How do you profile the pages? I mean, how does the kernel know whether a page is hot or cold? Do you perform some kind of offline profiling?
No, in this case, the operating system is annotating when pages are hit and moved. So you have the information actually from the kernel.
I see. Okay. Thank you very much.
Thank you.
Thank you, Antonio. Thank you for your contribution.